Morning. Today we're going to talk about objects in free fall, objects that are falling from some great height. And if you ask most people what would happen if I dropped a heavy object and a light object at the same time from the same height, most of them would probably reasonably say that the heavy object would hit the ground first. If I specified a bowling ball and a feather, I'm sure 99 people out of 100 would correctly say that the bowling ball would hit the ground first and the feather would hit the ground sometime later. And indeed, that is exactly what happens when you try this. You might wonder why anyone would even suspect that something different would happen. But when we watch our friend Emily drop a light rock, a small rock, hits the ground with some force, she does it again in case you didn't see it the first time, hits the ground, and we see it threw some dirt up in the air. When she drops a much heavier rock, you can see that it hit the ground with more force. There's no question it would hurt more if that landed on your foot. But what happens if she drops them at the same time? They seem to have hit at about the same moment, and they did. Now this seems a little strange. The bowling ball hit the ground before the feather did, but the small rock and the large rock, despite the fact that the large rock looks to be several times heavier than the small rock, seem to have hit the ground at the same time. This makes more sense when we look at the formula F equals m times a. Force equals mass times acceleration. There's no question that the mass of the large rock is greater than the mass of the small rock. And as a result, the force of the large rock hitting the ground is greater than the force of the small rock. But the acceleration is the same. They fell with the same acceleration, the acceleration due to gravity pulling on them. It's true that gravity pulls harder on the larger object, resulting in a greater force. But the acceleration from that gravity is the same. How can that be? If we look at an extreme example, an elephant and a mouse being dropped at the same time, we see that the elephant is falling with a tremendous force, but that's being divided by an also tremendous mass. If F equals ma, then A, acceleration, equals force divided by mass. A large force divided by a large mass gives us A. We get the same acceleration looking at the mouse. It's a much smaller mass being divided into a much smaller force. But the A, the acceleration, will be the same as that of the elephant. The scientist who gets credit for coming up with this equation is Galileo, one of the great minds of science. And he did the test where he dropped objects of unequal mass from a great height, supposedly the Leaning Tower of Pisa, and they hit the ground at about the same time. Now, he didn't have the kind of sophisticated tools we would have now, but it was enough to show that acceleration was the same. So if we drop a watermelon and another fruit of considerably less mass, they hit the ground and make a big mess at about the same time. But this takes us back to our feather and bowling ball. If it's true that falling objects fall at the same acceleration, why then did the bowling ball hit before the feather did? But if we look at them falling in slow motion, we can see that there are other forces at play. Look at how the air, the wind is moving the feather. Okay, if something moves, it's because there's a force. So there's clearly a force acting on the feather and probably on the bowling ball, but not to the same degree. And that is air resistance. The air is pushing up against the bowling ball and feather. It doesn't really have a whole lot of effect on the bowling ball, but the feather is designed to catch air, catch wind, and it has a tremendous effect. So then the question is, what would happen if we sucked all the air out of the room? If the bowling ball and feather were falling in a perfect vacuum with nothing there to hit them as they fall down, nothing to catch them, would they fall at the same speed? And amazingly, they did this in this room, and the result is pretty interesting. The bowling ball and the feather fell at the same speed. Their acceleration was the same because only gravity was acting on them. That was the only force accelerating them down. And gravity is 9.8 meters per second squared, no matter what you are. Take the air resistance out of the equation, and we all would fall at the same speed. Now, what this means is if you jump off of a great height, you should keep speeding up and speeding up because gravity doesn't stop, and it should just keep on accelerating you until you hit the earth at some phenomenal speed. But what really happens is you reach a certain speed and you stay at that speed. We call that terminal velocity. Terminal velocity is what we see with the skydiver here. He jumps out, and at first, gravity is pulling him down, and the push of the wind against him is not that great. But there comes a point pretty quickly where he's being pushed by the air just as hard as gravity is pulling him down. Now, he doesn't stop, but the forces now are equal. They are balanced. And a balanced force results in no change in motion. So he's falling at about 120 miles an hour, and he will stay at that speed, not getting greater or less until finally he hits the ground or pulls his parachute. Now, if we look at terminal velocity in a skydiver here in this diagram, first he jumps out, and because of his mass, he's being pulled down with a force of about 830 newtons. After a short period of time, as he's falling, the air is now pushing against him with a force of about 350 newtons. But still gravity stays the same. So there's 830 newtons pulling him down, and there's 350 pushing him up. They're unbalanced, but it's unbalanced in favor of continuing to accelerate. So he's still accelerating. After another moment, now the air, because he's going faster, the air's hitting him harder. So now there's 700 newtons of force pushing upward, but still 830 pulling him down. So he continues to accelerate, but he's accelerating at a slower rate. He is speeding up, but not nearly as fast as he was in the beginning. And then finally, he reaches the point where the air pushing against him is 830 newtons. Gravity pulling him down remains at 830 newtons. He is now balanced. Whatever speed he has achieved at that point is the speed he will stay at. Balanced forces don't change motion. Now, another way of looking at it is this one, where the green arrows represent the forces. The skydiver is being pulled down by gravity. We have the green arrow there, and then we see a smaller green arrow appear going in the opposite direction. This is air resistance, a kind of friction, fluid friction. And eventually they are balanced. They are the same size, and he's falling at about 120 miles an hour. Now he pulls his parachute, and look what happens. By pulling the parachute, creating a much wider area for the air to catch, the air resistance becomes a stronger force than it was. It's a much bigger force than the gravity pulling him down. And if we have unbalanced forces, we have acceleration. In this case, he's accelerating in a negative way. He's slowing down. His velocity is going from 120 miles an hour lower and lower and lower until once again, the two forces are balanced. Because he's slowing down, the air is not pushing against the parachute as high. So actually the force going upward, the air resistance decreases as he slows down until finally it again balances with gravity, and the speed that he's at that point, about say 15 miles an hour or so, is the speed he will stay at until he comes down to the ground. A much better speed if you're hoping to survive the skydiving experience. So in conclusion, the two things that they would like you to know about this part of the motion unit is that students will understand any two objects dropped from a height will have the same acceleration of gravity. Barring air resistance, they will fall at the same speed. Now, because there is air, you're going to see the result that if we drop an elephant and a mouse out of an airplane, the elephant will land first because the mouse is going to be much more affected by the air resistance and the wind than the elephant would. If we drop them both on the moon, they would hit at exactly the same time because there's nothing there. This also points out why it would be a really bad idea to go skydiving on the moon. Since there's no air, you'd start falling. Now, the moon doesn't have as much gravity. You'd be falling at a slower rate of acceleration, but you would keep accelerating. And unlike on Earth, there'd be no wind to slow you down. You would just keep speeding up and speeding up. Pull the parachute all you want. There's no air to catch the parachute. It's not going to make any difference, and you will just keep increasing your speed until you slam into the moon and make a new crater. So the second point they wanted you to know is recognize that air resistance is a force that is moving against a falling object, and causes it eventually to come into balance with the force of gravity, which doesn't change, pulling down until finally they have achieved a balance, and that speed that you stay at is called terminal velocity. Thank you, Emily Basilos, for helping out with this video, and I'll talk to you guys more about this later. Bye now.